Hi everyone, my name is John and my teammate is Jacob, and we are presenting on the automated greenhouse. In this presentation, I'm going to talk about the hardware electrical schematic and how it works with the software. And my colleague Jacob will talk about how our circuit behaves in every situation. So the goal of our project is to monitor temperature, humidity, and soil moisture. And to achieve this goal, we have the DHT11, which is our humidity and temperature sensor. And also on the right, we have our soil moisture sensor. For the actuators to achieve our goal for this project, we have a water pump, which is here on the far left, and on the middle, we have a humidifier, and on the far right, we have the fan. And more on the actuators, we have the sieve motor, and we also have the heater. So other electrical components that we have the 4-channel relay to control our actuators, and we have our LCD here, 16:2, to display current, humidity, and temperature. And we have our Raspberry Pi Pico, which is our microcontroller. So here is our schematic for our project with all components put together. Here on the top, we have our actuators. We have a water pump, humidifier, heater, and the fan. And also on the actuators, we have this sieve motor here. And for the sensors, here is one of our sensors, which is the DHT11 temperature and humidity sensor. And here we have the soil moisture sensor. And here we have the LCD to display current, temperature, and humidity. And this is our Raspberry Pi Pico, which is our microcontroller. And this is our 4-channel relay to control our actuators. So here's what our circuit works, how our circuit works. I'll start with the DHT11, which measures temperature and humidity. I'll start with the humidity. So the DHT11 measures the humidity inside our greenhouse, and it sends data to the Raspberry Pi Pico. The Raspberry Pi Pico processes the data and checks if within the threshold. Our threshold for humidity is 75% to 85%. If, for example, the humidity is below the threshold, which is 75%, the microcontroller will process the data and send a signal to the 4-channel relay to activate the humidifier or atomizer to raise the humidity to 75%. Once the humidity is 75% and above, the microcontroller will will send a signal again to the 4-channel relay to turn off the humidifier. For the temperature, again, the DHT11 measures temperature inside our greenhouse and send the data to the Raspberry Pi Pico. The Raspberry Pi Pico again process the data and check if it's within our threshold, which is 20 degrees and 30 degrees. If, for example, the temperature is above our threshold, which is above 30 degrees, our Raspberry Pi Pico will send a signal to the 4-channel relay to activate the fan to turn on. Once the fan turn on and temperature goes below 30 degrees, our our Raspberry Pi again will send a signal to turn off the fan. If the temperature is below our threshold, which is 20 degrees, the Raspberry Pi Pico again will send a signal to the 4-channel relay to turn on the heater to raise the temperature to above 20 degrees Celsius. And all our humidity and temperature values are displayed on the 16:2 LCD. So for the soil moisture sensor, our soil moisture sensor, it works with capacitive resistance. So the soil moisture sensor have different capacitive resistance in wet soil and in dry soil. So any capacitive resistance of the soil which is above 65, which is 60,000 and above, it means the soil is wet. Sorry, it means the soil is dry, and any value below 60,000 capacitive resistance, it means the soil is dry. So, for example, if our soil moisture detects that the capacitive resistance of the soil is, let's say, 61,000, it means the soil is dry. It will send a signal to the Raspberry Pi Pico, and the Raspberry Pi Pico will send a signal to the relay to turn on the pump. Once the soil become wet and the capacitive resistance drops down to below 60,000 capacitive resistance, the Raspberry Pi Pico again will send a signal to the relay to turn off the pump. And our servo motor here helps to control the humidity. If for some reasons the humidity inside our greenhouse goes to above the threshold, which is above 85 degrees, we designed our socket to, we designed the servo motor to turn to 0 degrees, and by doing that, it's going to open the window inside the window attached to the, it's going to open the greenhouse window, and by doing that, dry air will come in and neutralize the more humid air inside the greenhouse. Once the humidity drops to 85 to, once the humidity drops below 85%, the servo motor will turn to 90 degrees, and by doing that, it's going to close the window. And this is it for this presentation. Thank you.
Hello everyone, my name is Jacob Showerman. For the next section of this video, I will be guiding you through a demonstration of our Automated Greenhouse Control System, or the AGCS. A quick disclaimer for the format and flow of this demonstration. So the conditions being monitored are not easily observable and very slow to change. So due to this, I will be jumping around from boundary state conditions in the video to avoid making our viewers watch our enclosure's temperature and humidity conditions change over several minutes. All right, now we continue. So you can see as we power on our system, the LCD screen will display this welcome message and then transition into displaying live temperature and humidity values within the enclosure. This demonstration was filmed in the SJSU MLK library, so ambient conditions were too high of a temperature and too little humidity. We can see the system reacts to this accordingly by immediately kicking on the fan and the atomizer upon power up. Now moving forward, we can see that once the humidity inside the enclosure reaches that 75%, the atomizer is going to shut off. Notice how the fan still remains active as the temperature is not yet decreased to within the allowable threshold. So for the sake of John and I's time, we went ahead and placed the temperature sensor into a cup of ice to demonstrate the fan shut-off function. So you can see how once the temperature falls within that allowable range, the fan's going to go ahead and shut off. Now if we leave that sensor in the ice for an extended period of time such that it falls outside the allowable range, again, this time on the lower end, we should see this red LED inside the enclosure illuminate like so. Now, a quick aside, this LED is holding the place of a heater, which would raise the enclosure temperature back into the allowable range. Now, unfortunately, a heater was not able to be acquired for our project, so we utilized this light to show the microcontroller allowing a signal to be sent where the heater would fall into the circuit. Anyways, moving forward, we utilized the second sensor in the project and the fourth actuator when monitoring and maintaining soil moisture content. So similar to the heater situation, our enclosure does not have soil to monitor the moisture levels of, but for this demonstration, we are simply showing that when an absence of moisture is detected, the pump will activate and deliver water to the enclosure. You can also see how once the sensor is placed back into a moisture dense environment, the pump shuts off, like so. And lastly, we have examined all conditions except that in which the humidity rises above that allowable threshold. And this is where the servo motor comes into play. You can see here that as the humidity passes outside of that threshold, our motor attempts to swing the window all the way open to allow the moisture out and dry air in. Now clearly the window is not fully open, which exemplifies how this aspect of our project is in fact our biggest shortcoming. We were unable to dedicate the time required to meticulously ensure the window's smooth open and close operation. This is due to its tight fit in the close position, and our servo motor unfortunately lacks sufficient power to fully open and close that window. However, this failure is not from any mechatronics shortcoming, so we still consider this a success as the code, sensor, and actuator all performed as intended. Now this is going to conclude the examination and demonstration of all of our system states which allow the AGCS to function.